Hello, today's lecture we'll be looking at geologic dating the rock record. So uh, first we look at frames of reference. So we can date rocks using relative dating, which is when we determine the age of rock relative to other rock around it. For example, this rock is older than this rock, that rock, but it's younger than this other rock. Then there's absolute dating, when we determine the absolute age of the rock. And correlating rock units is whenever we draw time equivalencies, which means we can say that this rock and that rock formed at the same time between two rock units, which is useful if we know the age of one rock, but we don't know the age of another. If we're able to correlate them together, then we can assign that age to the unknown, the rock of unknown age. And then, we divide rocks into certain periods of time, and that time is organized using what's called the geologic time scale. So I don't really go too much into the geologic time scale in this class, physical geology. That's more for historical geology, which will be taught in the summer if you are interested. Summer session 1 and summer session 2. By me, I'll be teaching it. So the principle of superposition. So first we're going to start with, the principles of relative dating. So determine the relative ages of rock. Now a lot of these might seem kind of like common sense. Maybe like, well, duh. But at some point in time, someone had to sit down and think about this. It's like, well, which rock is older and which rock is younger? And they had to think it through. So we're going to go through several principles of relative dating, which will allow us to determine the relative age of rock. So the first is the principle of superposition. So what that is it states that in an undisturbed succession, which is a layering of sedimentary rocks, the oldest layer is at the bottom and the youngest layer is at the top. So here you can see this is the wall of the Grand Canyon. This is the wall of the Grand Canyon, right? And so here's an illustration of those beds of rock. So this rock is at the bottom. So it is the oldest. This rock is above it, so it's younger than this rock. But this rock is older than the rock above it. This rock is younger than the rock below it, but it's older than the rock above it. And this rock is younger than the rock below it, but it's older than the rock above it. So this is the youngest rock, and this is the oldest rock in this outcrop. Okay, that's the principle of superposition. Pretty straightforward. Principle of original horizontality. So horizontality, that states that whenever sediments are deposited, they're usually deposited by water, right? Most sedentary environments involve water. Whenever sediment is deposited, the principle of original horizontality states that sedimentary rocks are originally horizontal. So if we ever find sedimentary rocks that are tilted, they did not form that way. They were originally horizontal, and then they were tilted. Okay. If we find sedimentary rocks that are folded, like these ones, then we say that those rocks did not form that way. They are originally horizontal, and then they were folded. Okay, you can see the folds in this rock. See the beds, how it comes up here, this bed. And then where does it come on the other side? Actually, I don't see that one. Oh, is that right here? Yep, it's right here. And this bed, that's really cool. You can see it on this one. It's folded over and it comes down here and then bend back up there. It's cool to see rock just folded like that. So the next principle is lateral continuity. So this principle assumes that layers of sedimentary rock are continuous, right? They continue, they don't just disappear. One rock just doesn't all of a sudden disappear, like transition to another one. And that if layers of sedimentary rock are originally continuous, except where they thin and pinch out at the edge of a depositional basin like they do over here, or whenever they grade out, which means they transition into a different type of sediment, like what's happening right here. So this allows us, in examples like this, where this is a cross-section, this is a canyon, so the walls of the canyon have some limestone, shale, and sandstone on it. You see on the other side of the canyon, you have limestone, shale, and sandstone as well. Like, well, was there limestone here? Was there shale here, and did the sandstone? Well, the principle of lateral continuity says yes, that we don't expect that calcareous ooze is deposited here. For some reason, it was not deposited at this location, but was then deposited here. Now we assume it was deposited all through there, right? Same thing with the shale. It was deposited all through here. They're laterally continuous, and that this rock has been since removed by weathering and erosion. Cross-cutting relations. So this principle states that if there's a feature, such as a fault, as you can see here, that cuts across these layers of sedimentary rock, see how that fault is cutting across that layer. There's actually some offset. This is moved up, moved down. A fault or an igneous intrusion, so this igneous intrusion, these intrusions intruded into this sedimentary rock over here, then those features must be younger than the rock they displace, right? That makes sense, because in order for a fault to exist, the rock had to exist first before it could be faulted. The fault has to be younger than the rock. And with igneous intrusions, if molten rock is going to intrude into a rock, the rock it's intruding to must have existed first in order for the molten rock to intrude into it. Right? There's only one little ambiguity in this, is if there's a horizontal layer of igneous rock with sedimentary rock below it and above it. So in this case, you have sedimentary rock layers 1, 2, 3, 4, 5, with a lava flow, a layer of igneous rock in there between layer sedimentary rocks 2 and 3. The same thing here, sedimentary rock 1, 2, 3, 4, 5, and you have a layer of igneous rock. The difference is rock 3 is younger than the igneous rock in this situation, but here rock 3 is older than igneous rock in that situation. Why? Well, this is a lava flow, which means this is molten rocks that flowed over the surface. So rock 3 didn't exist yet. And then once it solidified, the sediment was deposited on top of it and then formed rock 3. Where this was a sill, which is an intrusion, which means rock 3 and 2 already existed, and this molten rock intruded in between those rocks. It means that rock 3 would have already existed before the igneous rock formed. How do you tell the difference? We see the shaded area below and above the sill. That's the metamorphic aureole, or the baked zone. It's the zone in which the heat from the molten rock metamorphosed the surrounding rock. We see the sill has a baked zone both below and above, because both the rock below it and above it were there whenever it was molten rock, where the lava flow only has a baked zone beneath it, because the rock above it wasn't there, never had formed. So here you can see that a horizontal layer of basalt, and it's a lava flow, not that you can see from this photo, but up close, if you look at the rock right beneath it, it is thermally metamorphosed, right? But the rock above it is not. So which tells us that it was a lava flow and not a sill. Next is the principle of inclusions. So sometimes we find pieces of one rock inside another rock. So for example, here we have igneous rock. This is metamorphic rock over here. We have these layers of sedimentary rock there and there. Well, pieces of the metamorphic rock are in the igneous rock, right? So the igneous rock is said to be hosting inclusions of the metamorphic rock. Likewise, this layer of shale is hosting inclusions of the metamorphic and the sedimentary rock. Well, according to the principle of inclusions, the host rock is always younger. That means is because the igneous rock is hosting inclusions of the metamorphic rock, the igneous rock is younger and the metamorphic rock is older. Because the shale is hosting inclusions of igneous rock. The shale is younger than igneous rock. Igneous rock is older. You see here, the shale is hosting pieces of metamorphic rock. So it says the shale is younger and the metamorphic rock is older, which makes sense because we already established that the shale is younger than the igneous rock and that the igneous rock is younger than the metamorphic rock. So therefore, the shale would have to be younger than the metamorphic rock, which these inclusions tell us it is. All right, so that's the principle of inclusions. The host rock is always younger. Next brings us to unconformities. Now, this isn't a principle of relative dating, but it's something we find in the geologic record. So we assume that in a sedimentary environment, that sediments are continuously being deposited. And so here we have time. This is going, forward in time this way, from 12 million years ago here to present day here. And now sediments are continuously being deposited, forming all these different layers of sedimentary rock. And so a record is being collected. The environment is there because the type of sediments are deposited, what organisms are living there, for what type of fossils we find. So we have this continuous record being recorded. However, at about 4 million years, something happens. No more sediments are being deposited in this area. And in fact, for 1 million years, not only is no sediment deposited, but rock is weathered and eroded. And so then you have actually, during that 1 million years, this rock is removed. And so you have this erosional surface, this rough, undulating surface that's left by erosion. And then after that 1 million years of weathering and erosion, sediment deposition resumes. So sediment deposition stopped at 4 million years. There was weathering and erosion for 1 million years. And sediment deposition resumed after that. And so there's a gap here in the record. Not only do we have the 1 million year in which no sediment was deposited, then you have the time of that is represented by the rock that was removed by the erosion. So in the geologic record, you have this hiatus or this gap in time. But you don't see this gap because this sediment is deposited right on top of that erosional surface. So what you see is this boundary between rocks that don't conform, right? This rough surface, this rough contact, and it might be like one sort of environment, like maybe I'll say conglomerate, and then on top of the conglomerate is, sandstone. It's like, well, how does it go from glacial environment or the base of a mountain to a beach just like that, all of a sudden? It doesn't. There was a lot of time there that's just missing. And so the oldest rock that was remaining after the erosion was the conglomerate, and then the sand was deposited on top of it at a later time, forming the unconformity. So these unconformities here represent a hiatus or a missing gap in time. And so, for example, in this one, there's 3 million years missing, which we don't know how much time is missing unless we know the age of the rock below it and above it. So I like to use the analogy of the Dark Ages, right? So the Dark Ages are a period in history in Western Europe where we don't know a lot because after Rome fell, civilization kind of took a couple steps backwards, and a lot of people weren't literate. They couldn't read or write, so there wasn't a lot of records being kept. And so we have a good record coming out of Rome, right, up until the fall of Rome. So we have this record, and something happens. Civilization, as I said, stumbles a little bit, and we have this very sparse period of time where there's not really a good record. So we call them the Dark Ages because you don't know too much about what happened. But then we have the Renaissance, and the record picks up again, right? We have more education, reading, writing, literacy, and so our record picks up again. So with that period of time, the Dark Ages, they kind of represent, they're similar to a hiatus, period of time in geologic past, which we don't know much about what happened because there's no rocks from that time, because no record. It was either being kept due to a lack of sediment deposition, or there, in addition to rock that might have already been there, is removed by weather and erosion. And that no sediment deposit. So there's I like to say with this slide, there's 3 types of unconformities, and there's a lot of text on this slide. Right? We can go through the definition of each of these one by one, but the 3 types of unconformities are disconformities, angular unconformities, and nonconformities. Right, so first we're looking at disconformity. A disconformity is an unconformity that separates older from younger parallel layers of sedimentary rock. Okay, so they don't have to be horizontal like it says here, they just have to be parallel. So you see how these rocks are parallel to the rocks above them? That's a disconformity. Right here's the unconformity itself, the erosional surface. So how does a disconformity form? Well, first we have to form the older rocks. So there's sediment deposition in this area, form the older rocks. Then we have to have weathering and erosion. So there's uplift, so the region is uplifted probably due to some tectonic activity, like a convergent plate boundary nearby, it's pushed up, and there's weathering. So this rock is removed, and this rock is weathered into, forming this erosional surface. Right? Then sediment deposition resumes, and younger sedimentary rocks are deposited on top of the erosional surface, forming a disconformity. So here we have sedimentary rocks that formed during the Mississippian, and then more sedimentary rocks directly on top of them that formed during the Jurassic. And so there's a couple 100 million years in between those 2 periods of time in geologic history, but they're right on top of each other. What that means is there's a gap in there. And because these rocks are parallel, it's a disconformity. The next type of unconformity is an angular unconformity. An angular unconformity is an erosional surface that exists in either tilted or folded older sedimentary rocks and overlain by younger horizontal sedimentary rocks. So here's the older tilted or folded, these ones are tilted, and then the younger ones are horizontal. So there's an additional step here than there is in the disconformity, where the older rocks have to be tilted or folded. So how do we form an angular unconformity? Well, first we have to form the older sedimentary rocks. Now remember, the principle of original horizontality tells us that those sedimentary rocks were originally horizontal. When something happens, a tectonic activity where it's uplifted, in this case it's tilted, or it could have been folded. Then there's weathering and erosion, so it erodes down, creates an erosional surface, and then sediment deposition resumes, forming the angular unconformity. All right. So here you can see there's an angular unconformity right here. And you see the bedding planes are this way. It's almost up and down. So that means they're tilted almost 90 degrees. And then these ones are running that way. There's a better look at one here. These beds of sandstone are running this way. They're not horizontal, they're tilted. And here's the unconformity of the erosional surface on which it looks like this breccia was deposited. Our last unconformity is a nonconformity. Nonconformity is erosional surface in igneous or metamorphic rock that's overlain by younger sedimentary rocks. So how does a nonconformity form? Well, first, the igneous or metamorphic rock has to form. So here there's an igneous intrusion. Then there's uplift and weathering and the erosion, removing all the overlying sedimentary rock, and the igneous rock is weathered as well, forming an erosional surface. And then later in time, it becomes a depositional environment again, and sediments are deposited on top of the erosional surface in the igneous or metamorphic rock, forming the nonconformity. And here's an example. So most places you go, there's a nonconformity because the really old rock in the continents are igneous or metamorphic rock from the Precambrian. And on top of it, younger sedimentary rocks are deposited. So these are Precambrian metamorphic rocks with younger sedimentary rocks deposited on top of them in this photo. So here we're looking at a cross-section of part of the Grand Canyon where we can see several unconformities. So here we have those Precambrian rocks that I just talked about. They're metamorphic and igneous rocks. And so here, this is a nonconformity because this is an erosional surface in this igneous or metamorphic rock, which sedimentary rock is deposited on top. Now notice that this sedimentary rock here, it's tilted, right? So the erosional surface in them is an angular unconformity. So this is an angular unconformity. And these rocks are parallel to each other. So the unconformity between them is known as a disconformity. And the same thing here, these rocks and these rocks are parallel to each other. So this unconformity between them is a disconformity. The newest unconformity is the surface, right? No sediments are being deposited in this area. So this is slowly being weathered away. So over time, more and more of this rock will be weathered away. And who knows how much will be weathered away until sediment deposition resumes in this area. And we could have the next unconformity. So we can apply the principles of relative dating to reconstruct the geologic history of an area. We can't apply any specific dates, but the relative sequence of events can be determined using these principles of relative dating. For example, we see this geologic section right here. Looks like there's a lot going on, but all the rock units are labeled sedimentary rock A, B, C, E, G, H, I, J, and K. And then we have igneous rocks D and F. Sedimentary rocks are tilted, and we see an unconformity there. Right? So what's first? Well, superposition tells us the oldest rocks are the deepest rocks. So that's A. Then next youngest to be on top of it, B. And then C. And why not D? Why does it skip D but E? Well, because if you see, D has pieces of E and C in it. So the principle of inclusions tells us the host rock is younger. Because D is hosting inclusions of E and C, D must be younger than them. That's why E formed after C. How is that possible? Well, D is an igneous rock. It's a sill, so molten rock intruded in between E and C, as we see in step 2. Now we see after D, F cuts through everything up to and including E. That means F is younger than everything up to including E. So F is an intrusion that cuts across them, cross-cutting relations. It doesn't cut across anything else. Right? And you actually see F is actually cut off by this erosional surface. So after F, the sedimentary rocks were originally horizontal, right? Must have been tilted. So we have the tilting and then the erosion. And then the younger sedimentary rocks were deposited on top of that. G, H, I, J, K. Okay. So we see this geologic section is pretty complicated, but it's not that bad. We have a bunch of different units of bedrock. Most of them are sedimentary. Some of them are igneous. The only igneous ones are F, R, and A. We have a couple other features. We have this fault right here. This fault right here is labeled I. This, oh, my laser pointer stopped working. This unconformity right here is labeled J. This unconformity is labeled H. And this other part of the same unconformity is labeled P. The only feature that's on here that's not labeled is the tilting of the sedimentary rock. So we can go through, we can rank the oldest from the youngest. So I'll start with the oldest with 1, and I'll work to the youngest, okay, with increasing numbers. So superposition tells us the deepest rocks are the oldest. So if we go deep, we see there's B, right? That's the oldest. So B is the oldest, so we're at a 1 there. And then on top of that is the next youngest, so B, then S. Then G, then T, then M, then C. Oh, I should have wrote 4 there. Oh, sorry, 5, not M. Not very helpful, right M next to M. We said C was next, it'd be 6. Then O. Then that stops. That sequence stops. So superposition, remember, applies to an undisturbed sequence. So then that sequence becomes disturbed. Well, we see that what's right above it? Well, there's this rough surfaces, erosional surface. There's an unconformity. You know, there's uplift, weathering, and erosion. But there's also these rocks, B through O, are not horizontal. And we know the sedimentary rocks are originally horizontal. And they're tilted now, so they must have been tilted. And there's also this fault. This fault cuts through B through O, so it must be younger than B through O, but it doesn't cut through anything else, so it must be older than that. So in 8, we can have the tilting, and then 9, the faulting, but those could be interchangeable. We don't know which one happened first. They could have tilted then faulted, or faulted then tilted. But after that, we know that after the tilting and the faulting, then we have this erosions, angular unconformity. So 10 is J, that's uplift and erosion. Makes sense, because usually whenever rocks are tilted, that means they're pushed up, right? And so there's usually uplift and erosion. That erosion could have started before the tilting. No, it usually starts after the tilting. Sorry, after it's tilted, then it begins to erode, erosion. Then next we have E. So E is the more sedimentary rocks, the sediments are being deposited. Then N, and then L. You can see now this unit A, it cuts through everything up to, including L, but nothing more. This is igneous intrusion, molten rock, so it's a cross-cutting relations. It says that it's younger than those rocks, everything up to L. So 14, igneous intrusion. And then above it, we have this erosional surface, so it's unconformity. Right, so for 15, we have weather uplift and erosion. And form the unconformity, H and P. So H is a disconformity, P is a nonconformity. And after that, we have D. So D would be 16. Q would be 17. Now R cuts across everything up to and including Q. So R must be younger than Q. But we also see that F is younger than Q because it's on top of Q. But R and F don't interact with each other. So we don't know if F is younger than R or R is younger than F. So we don't know the sequence, but we do see K on top of F. You know, K is sedimentary rock, so it must be younger than F because there's no big zone up here. So it could go for Q, could go 18, 19, and then 20. Or, so that would be R, FK, or it could be FKR, or it could be FRK. It could be in any order, those last three, but we just know that it has to be younger than Q, and K has to be younger than F. But so how we can put together that sequence of events applying those principles of relative dating. We do the same thing here, where we have the blue rocks. These rocks right here, they're metamorphic rocks. The brown rocks, those are these. Excuse the noise in the background. You hear it. The green rocks, the red rocks. These are the gray rocks right here. And these are the black rocks, which kind of look brown. And we have 4 unconformities, 1, 2, 3, 4, and a fault. So superposition tells us the deepest is the oldest. These metamorphic rocks are the oldest. So it's the blue. And then we have the unconformity. right? There's unconformity on top of it. The one of those unconformities is next. Then we have the brown rocks, or deposited. So that would be two. Then we have the unconformity. That's uplift and erosion. Then the brown rocks. The brown rocks are sedimentary rocks. You can tell that because they're in beds. You can see how they're tilted, folded. They didn't form that way. They're originally horizontal. So they must have been folded. So the folding comes next. And then you can see these gray rocks intrude into the brown rocks. So they cut across them. So the gray rocks form next to those igneous rocks. And then the gray rocks and the brown rocks are eroded. So we have our second unconformity. So the gray rocks, we have 6. Unconformity is uplift and erosion. Then we have the green rocks, more sedimentary rocks. Then another unconformity. That's a unconformity. Then we have the red rocks. And then we have, oh, nope, I missed something. For the red rocks, we have these. Oh, we have the black rocks. So the black rocks, that's 9. And then we have the weathering erosion, the unconformity, 10. And then the red rocks. And then the last unconformity. And then finally, we have the fault. So this works. This is a hyperlink. I don't know if I can open it. It seems to be a little wonky right now. All right. Yeah, I guess I can't open it right now. But if you go on Blackboard and look at these sites, you might be able to look at this where it's an animation. It goes through a sequence of events that you can look at and you can compare it to what we went through there. You see how it all unfolds. So I see this geologic section here. And so using relative dating, we can kind of piece together a sequence of events. Oops. So what relationship describes the relative ages of rocks to location A, location B? Is it A is older than B is older than A and B are the same age, or there's not enough information to determine a relationship? Well, superposition tells us that rocks at the bottom are older, rocks on top are younger. So superposition would tell us that B is older than A. So the answer would be B. Here we have these lines that help illustrate the bedding of sedimentary rock. So you can clearly see that these rocks are folded and these rocks are more horizontal up here. What is that red line? Is it a fault, an unconformity, or a convergent plate boundary? Well, you can see how this bed gets cut off. This bed gets cut off. So it must have been removed by erosion. So this is an erosional surface. right? It is an unconformity. What type of unconformity? Well, because the older rocks are folded, that's an angular unconformity. What event did not happen in this area? Sediments were deposited. Well, these rocks were in beds, they're sedimentary rocks. These rocks are in beds, sedentary rocks. So in order for them to be sedimentary rocks, sediments must have been deposited. Each sediment turns into rock. Well, in order for there to be sedimentary rocks, the sediments had to be turned into rocks. Rock was folded. You can clearly see the folds. Rock was metamorphosed. I don't know about that. But E says rock was eroded. And we know in order to form this unconformity, rock had to be eroded. So the process of elimination tells us that rock was not metamorphosed here. That brings us to absolute dating. So absolute dating is how we determine the absolute age of rock. We determine it in years before present. Okay. And so how we determine the absolute age of rock is using what's called radioactive dating. So if you remember, we talked about matter and minerals. The structure of an atom is the nucleus and has protons, which have a positive electrical charge, and neutrons that have no electrical charge. And surrounding the nucleus is the electrons with a negative electrical charge. Now remember, like charges repel each other. So the positively charged protons packed inside the nucleus push away from each other. The only thing that holds them all together in the nucleus are the neutrons. The neutrons act kind of like a nuclear glue. Well, what happens is if you have a really large atom that has a large number of protons in the nucleus, well, sometimes there's not enough neutrons just to hold all those protons together. What happens is they push away from each other and the nucleus falls apart. That tendency for an atom's nucleus to basically fall apart, that makes that atom unstable. And we call that process of an atom's nucleus breaking down into smaller pieces. We call that radioactive decay. Any atom that undergoes that or exhibits that behavior is said to be radioactive. It's basically unstable. And so larger elements with a large number of protons in their nucleus tend to be radioactive elements, like uranium. Uranium is the largest naturally occurring element with 92 protons in its nucleus. Right? And so often there's different number of neutrons than protons in the nucleus. And we call those isotopes. Any atom that has a different number of neutrons than protons is an isotope. And there's many different isotopes of an element. So for example, if we look at uranium, there's one isotope called uranium-235, and it's abbreviated U-235. And what's that 235, that number? That's the number of the nucleons. And the nucleons are the particles in the nucleus, the neutrons and the protons. And so if it is uranium-235 and uranium has 92 protons, well, 235 minus 92 means U-235 has 143 neutrons. Another common isotope of uranium is U-238. Because that's supposed to be an arrow. And because in order for it to be uranium, it has to have 92 protons. It can't have a different number of protons. That we know that this has 3 more neutrons than U-235, so it has 146 neutrons. So which one do you think is more unstable, more radioactive, U-235 or U-238? You said U-235 because it has less neutrons, which act as a nuclear glue. You're correct. So U-238 is more unstable than U-235 is more unstable than U-238. So whenever we mine uranium ores, so minerals that have uranium in them, and we extract uranium, we get a combination of all different isotopes of uranium. These are being two very common ones. And then you have to separate the U-235 and U-238 if you want to, enrich that uranium for different purposes. If you enrich it to a certain extent for fuel grade to use in a nuclear power plant, and then you have to enrich it to a higher percentage of U-235 if you want it to be weapons grade to make a nuclear bomb. The way they enrich it is they spin it in a centrifuge, or the heavier U-238 goes to the outside, just like the denser components of blood go to the outside in the centrifuge, and the lighter U-235 goes to the inside, just like the lighter components of blood come to the inside in the centrifuge when you spin blood in the centrifuge. So that's why, if you remember, like the Iran nuclear deal, they had to shut down a certain number of their centrifuges because they use centrifuges to enrich uranium. Anyways, I use uranium as an example because most people are familiar with uranium, at least they heard of it, and it illustrates radioactive decay. All right? So, when an atom, a radioactive atom, decays, right, it forms, it's kind of like a chain, a tree. So the radioactive atom itself is called the parent. It's called the parent. We call it P. And it breaks apart, okay? It forms other atoms because, it's a nucleus. The nucleus is breaking apart. And so some protons go this way, some protons go that way. Well, there's a different number of protons now in those two clumps, so those makes two different elements. And say one of those elements, it itself is radioactive, so it decays away into smaller pieces. And then maybe one of those decays away, smaller pieces. But eventually, whenever it decays into an atom that has a stable, it has a number of protons that's stable, those are called stable daughters. Okay, stable daughters. And so radioactive parents decay into stable daughters. Now, physicists, after studying radioactive materials, they learned that radioactive elements, they decay away or they break down at a predictable rate. And that rate is in a very predictable way. And that way is very easily characterized using a number called the half-life. So it's exponential, which means that it falls off a lot at first, and then it decreases more and more significant. It decreases less and less, more and more gradually, I guess, as time goes on. It's called exponential decay. But what happens is after each half-life, which is a certain period of time, now that's specific for each radioactive parent and stable daughter, but after each half-life, so here we see in this graph, the number of half-lives is on the x-axis. I want my pen. Where's my pen? The number of half-lives is on the x-axis, and this is the number of atoms present. So initially, at time t equals 0, we have 100% of the atoms are the parent, the radioactive parent. After one half-life, half of the parent decays away. So half of 100 is 50. So 50 of the parents decay away. Well, what do the parents decay into? They do excuse me. They decay into daughters. So after one half-life, we only have 50% remaining parent, but now 50% of the atoms are now daughters because the other 50% of the parents decayed into daughters. That's after one half-life. After two half-lives, half of this 50 will decay away. So half of 50 is 25. So 25% of the parent decays away, and that 25% of the parent decayed away became daughters. So now we have 75% daughters, 25% parents. After another half-life, half of 25 decays. Now this is in atoms. You can't have half of an atom, so 12 and a half, so it rounds up 13 atoms. And the 12.5% that decay away, they become daughters. So you see, after each half-life, half of the remaining parent decays away and becomes daughters. So if we look at the ratio of daughter to parent, that tells us how many half-lives have elapsed. So here, at 0, time t equals 0, the ratio, I'm going to draw it across the top, the daughter to parent ratio. Here it's 0 because there's no daughters. Here it's 1 to 1, all right, so it's 1. Here, there's 3 times as many parents as there are, 3 times as many daughters as there are parents, the ratio is 3. Here, there's 7 times more, the ratio is 7. Here, there's 15 times more, so the ratio is 15. So you can see, when we look at a sample, say a piece of, look at a mineral, we can crush it up and put the sample in what's called a mass spectrometer, which can measure the different amounts, how much there is of each element, even each different isotopes of each element. So you can measure the amount of parent and daughter in a sample, say a mineral crystal. And looking at the ratio of daughter to parent tells us how many half-lives have elapsed. If we know the half-life of that radioactive parent and stable daughter pair, then we just simply multiply the number of elapsed half-lives by the length of that half-life. So for example, I think the half-life of uranium-235, that one of its stable daughters, lead-207. Sorry for the, is about 700 million years. 700 million years is the half-life for uranium-235. Give me 1 second. So since the half-life of uranium-235 to lead is about 700 million years, let's say the sample, it said that we had 3 to 1 daughter to parents. That tells us that 2 half-lives have elapsed. And since 2 half-lives elapsed, we take the number of half-lives multiply it by the length of 1 half-life that gives us the age of the rock, how long ago that mineral crystal formed. So in this case, we had 2 half-lives times 700 million years gives us 1,400 million years, or 1.4 billion years. So the wonderful thing about this is whenever rock melts, the parent and the daughter atoms, they separate because they're not the same, because the daughters are obviously smaller than the parents. So they usually separate. So every time a rock melts, this radioactive clock is reset. And whenever a mineral crystal solidifies from melt, the clock starts ticking. And so this technique allows us to determine when minerals crystallized from melt, which means that we can determine the absolute age of igneous rocks using this. Now, we can't do it for sedimentary rocks, right? If we went to a bed of sandstone, we took a bunch of quartz feldspar crystals from that sandstone, we took them to the lab and measured their ages. Would we be measuring the age using radioactive dating? Would we be measuring the age in which that sandstone formed? No, we'd be measuring the age of when those mineral crystals solidified from melt. So we'd be measuring the age of the igneous rock from which they came. So we get all different ages, because that sediment was deposited there from water from who knows where. So we can't apply this to determine the absolute age of sedimentary rock. Same thing with metamorphic rock. When a rock was metamorphosed, yeah, it's altered, but the parents and the daughters aren't separated, so the radioactive clock is not reset. So radioactive dating can really only be applied to igneous rock. However, if we have igneous material around, which we can determine its absolute age, we can use relative dating to come to some conclusions about the absolute age of rock around it. For example, in this cross-section down here, this batholith, it's igneous, so we can measure its age 108 million years. And this dike, igneous, measure its age 150 million years. Now, relative dating tells us that these sedimentary rocks are younger than this batholith, but this dike is younger than the sedimentary rocks, so these sedimentary rocks are older than the dike, which tells us that these sedimentary rocks must be between 180 and 150 million years old. So we can apply that absolute bracket in time. We can know we are able to identify the absolute age of metamorphic rocks if we know the age of the event that metamorphosed them. For example, let's say we know there was a large continental convergence 750 million years ago, like the formation of a supercontinent or something that regionally metamorphosed a lot of rock. And so let's say that's what these are. These are sedimentary rocks that are regionally metamorphosed by a known event 750 million years ago. There's sedimentary rocks above it, and ashfall, more sedimentary rocks, lava flow. Ashfall and lava flow, igneous material. We can date it. We get an age, 675 and 600 million years old. So we know this sedimentary rock is younger than the 750 million year old metamorphic rock, but it's younger than that, but it's older than the 675 million year old ashfall. So that makes this sedimentary rock between 675 and 750 million years old. But these sedimentary rocks must be younger than the 675 million year old ashfall, but older than the 600 million year old lava flow due to superposition, which puts them between 600 and 675 million years old. So we can use relative dating along with known points in time from the absolute dating of igneous rock to come to some conclusion about the absolute age of sedimentary rock. What happens if there's no igneous rock around to provide us a reference in time? Well, then we have to look to the fossils. So over 99% of all species of organisms that have lived on this planet are extinct. Extinction is the status quo. So organisms come into existence through evolution and they go out of existence through extinction. And so in paleontology and paleobotany, there's this idea of fossil succession, that as organisms came into existence, they created fossils, and if they went out of existence, they no longer created fossils. And the fossils from that organism identify the period of time in Earth history in which that organism was alive. And so if a sedimentary rock, if two units of sedimentary rock have a lot of the same fossils in them, the same organisms, it's very likely that those sedimentary rocks formed in a very similar period of time. Let's say, for example, these sedimentary rocks here at location A. We know the age of those rocks. And say this rock here, it contains these fossils in them. Well, location B and C, we don't know the ages of those rocks. But we know that these rocks at location B, they have the same fossils as the rocks at location A of known age. What that allows us to do is to correlate these rock units together in time. Say, okay, now these rocks must be the same age as these rocks at A, so we can now prescribe that age to these rocks. So now we can put that age to these rocks at location B, and also, by virtue of the same principle, to these rocks at C. However, these rocks down here at location C have different fossils in them, then likely formed at a different time. So these rocks at C must be older due to superposition than these rocks over here at A. And these rocks at location A contain these fossils, as do these rocks at location B and these rocks at location C. That allows us to correlate these rocks together and map the time from A to B and A to C. However, these rocks at B contain different fossils and must have formed at a different period of time, and therefore must be younger than these rocks because of superposition, they're above them. So that's one way. If you have sedimentary rocks of a known age, you have the fossils in them, then you can correlate those ages to other nearby sedimentary rocks that contain the same fossils. But what if we don't even have any sedimentary rock of known age around? All we do is we have sedimentary rock with fossils in it. Well, like I said before, organisms come into and out of extinction all throughout history, and so the paleontological and paleobotanical record, we can use that to identify the time in Earth's past in which a rock formed. Because let's say rock unit A contains these fossils. Now this is just for proof of concept. There's no environment where a scallop, a T-Rex, a starfish, a maple leaf, and a fern all live together unless there was a large flood that deposited them all together. But let's say rock unit A had these 5 fossils in it. So now we look at the paleobotanical and paleontological record and say, well, what sliver or what portion of Earth history were all 5 of those species simultaneously present on Earth, according to the fossil record? You see, that indicates this period of time, which all 5 of them were around. So we have the scallop, the fern, the T-Rex, the maple leaf, and the starfish. Right, so that rock must have formed during that period of time. Same thing with rock B, it has these 5 fossils in it, which corresponds to this sliver of time. Depending on the fossils, you might be able to get a more specific or less specific period of time. Like you see, rock unit A, those fossils give us a narrower window of time, where the rocks at B give us a wider period of time. But nonetheless, fossil succession allows us to be able to ascribe some absolute age to sedimentary rock as well. Also, sometimes we have these large beds of rock that are geographically very extended, so they cover a large geographic area, like the ashfall from a large volcanic eruption. They act as marker beds or key beds, which they give us a reference in time over a large area, and they're useful for dating. So like the Yellowstone eruptions are useful for North America. Other volcanic eruptions are useful in other regions. One of the most significant marker beds is this one right here, this on top. This is the KT boundary, which marks the Cretaceous, which they use a K to abbreviate Cretaceous, and T, Tertiary. Cretaceous is the last period of the Mesozoic, and the Tertiary is the first period of the Cenozoic. So the Mesozoic is known as the age of reptiles, right? That had the Triassic, Jurassic, and the Cretaceous in it. The Cenozoic is the age of mammals. So we currently live in the Cenozoic. But this period of time, this marker bed marks 65 million years ago. So because 65 million years ago, there was a mass extinction event. That mass extinction event brought the end of the Mesozoic. See all these different layers of sediment. It's really cool. And it's marked by the fallout of that event. What that event was, most of you know, was a large meteorite impact. That meteorite impact was so large it threw a bunch of debris up into the atmosphere. The atmosphere carried all across the globe, and it settled out onto the surface all over, and it formed this layer. And this layer is identified by having shocked quartz in it. As we talked about metamorphism, shocked quartz is what forms when there's a meteorite impact. And there's also high levels of iridium, which is an element found only in large abundances in the mantle and in asteroids. So anywhere, its KT boundary is found on all continents where these rocks of this age are present and sediments were being deposited at that time, at that location. And anytime we find this marker bed, we know, boom, we're looking at 65 million years ago. So if you're a vertebrate paleontologist and you're looking for dinosaur bones, you find this KT boundary, you're going to look down here, right? You're not going to look up here. You're wasting your time. And if you're a vertebrate paleontologist looking for Cenozoic mammal fossils, you're going to look up here. You're not going to look down here. You'll be wasting your time. Even though mammals did exist down here, they just weren't as abundant. Once the dinosaurs went extinct, then mammals began to flourish. But we talk all about that in historical geology. We talk about evolution and vertebrate evolution throughout this period of time, this larger period of time known as the Paleozoic. Sorry, the Phanerozoic. Sorry for the noise in the background. So correlating rock units allows us to piece together larger regions and get a larger picture of time. So for example, in the southwest portion of the United States, the region is called the Colorado Plateau. This area is known for the very vibrant, colorful bands or layers of sedimentary rock. Because for hundreds of millions of years, this was a sea floor on which layers of sediment were being deposited. And so up here you see Bryce Canyon National Park. You can see layers of sediment deposited. Zion National Park, layers of sediment deposited. Grand Canyon National Park, layers of sediment deposited. Well, this is Zion. Oh, this is, sorry, Bryce Canyon, Zion, and the Grand Canyon. You can see the rocks at Bryce Canyon. These rocks are young, or the oldest exposed rocks, right here, correlate with the youngest exposed rocks at Zion. So it allows us to draw this time equivalency. So what it allows us to do is say these rocks were likely here at one point in time and have since been eroded away. At the same time, these rocks down here are likely buried underneath here, just not exposed yet. And conversely, and additionally, the oldest exposed rocks at Bryce Canyon correlate to the youngest rocks at Grand Canyon. So, at Zion correlate to the youngest rocks still exposed to Grand Canyon. So these rocks were likely here, and these rocks were likely here, and these were likely here and here. Throughout, now we have this whole picture of time, not just these three small pieces in three different locations. We can put together this whole picture of time from the Cambrian, whenever complex animal life evolved on the planet, all the way up to the beginning of the Cenozoic. And so correlating rock units from one place to another and piecing it together allows us to put together a larger, more coherent history of a region, not just a location. All right. Now we're going to take a look at the geologic timescale. We're going to introduce it, get a feel for what was happening as far as life goes and the different eras of Earth's past. So you can see on the right this very colorful geologic timescale here. You see how it's organized by eons, and then eras, periods, and then epochs. You'll notice that there's more detail. Oh, I should say that this is present day right here. So that's today. And this is Earth's beginning. So Earth origin. Right, so this is 4,600 million years, or 4.6 billion years. It's important to know that the geologic timescale for a long time was a relative timescale, which means that we didn't know the exact times, the exact moments in time which one era, for example, ended and the other one began. So, for example, we knew that the Paleozoic, what happened in the Paleozoic occurred, say, before what the Mesozoic and after the Proterozoic, but we didn't know exactly when the Paleozoic was. That's because we made observations, on the planet, and using the principles of relative dating, we were able to put things in order. What happened first, second, earlier, later, and so we were able to put together this sequence of events in Earth's history. And we used the geologic timescale to keep it organized, which was really necessary considering that we didn't have any dates, because the technology, the ability to determine the age of rock using radiometric dating didn't exist, so we couldn't apply any absolute ages to anything. And so, for example, if there were rocks in the period of time which the dinosaurs reigned, well, those rocks were formed during the Mesozoic, because that's what really, it's one of the defining features of the Mesozoic. As we'll learn, it comes after a mass extinction, the Permian-Triassic mass extinction, and the Mesozoic ends at the Cretaceous-Tertiary extinction, or the KT extinction. So any rocks or anything that happened between those two extinctions were said to have happened in the Mesozoic era of the Phanerozoic eon. But we didn't know when that was. We didn't know when it began and when it ended. So looking at it, so we have two main eons. We have the Precambrian and then the Phanerozoic eons. Now you see the Precambrian looks small compared to the Phanerozoic, but you'll see that that's actually not the case when we apply absolute ages to it. But you'll also notice that it's much more detailed, as I said, closer to present day, and that's because one of the reasons is that complex life is around, so complex animal life is around for most of the Paleozoic, Mesozoic, and Cenozoic, what we call the Phanerozoic eon. And so there's a lot more fossil record during that time, so there's more detail in the geologic record, and also more of those rocks are still around today, because older rocks are not necessarily around anymore because they've been destroyed and turned into other types of rocks via the rock cycle. So let's take a look. Now this is the geologic time scale, and here it is with absolute dates applied. Now you can see how big the Cambrian is. The Precambrian. The Precambrian is actually the vast majority of Earth history. The Phanerozoic, that eon, it's very small. It's a little bit more than 500 million years. So it's a very interesting observation. So as I said, it was originally a relative timescale created before radiometric dating. And so since then, radiometric or absolute dates have been added, and that's how we get to this timescale, which actually has numbers associated. We have the Precambrian and the Phanerozoic eons. Okay, the Precambrian is subdivided into three smaller eons: the Hadean, the Archean, and the Proterozoic. The Phanerozoic eon is separated into three eras: the Paleozoic, the Mesozoic, and the Cenozoic. So Paleo means ancient, Meso means middle, and Ceno means recent. And you see that each of those eras are subdivided into periods. The Paleozoic has the Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, Permian. Then the Mesozoic has the Triassic, Jurassic, Cretaceous, and the Cenozoic has the Tertiary and Quaternary. Right, so you'll become more familiar with these as we go on. It kind of sounds like these weird foreign words. You might have heard some of them before, but some of them are probably out of left field. So we're going to look at the major parts of the geologic timescale and what was going on Earth during those periods. So first, we're going to start with the Precambrian. So this goes from 550 million years ago to 4,600 million years ago, the vast majority of Earth's history. Right? As far as life goes, life on the Earth is mostly bacteria-like life. So they're photosynthetic bacteria, and there's also some photosynthetic algae. And all this life lived in the oceans. Right? So no complex multicellular organisms really for most of the Precambrian. At the very end, Precambrian multicellular organisms arise at the very, very end. But for most of the Precambrian, and for them, or most of Earth history, life on this planet is microbes, little tiny bacteria and algae, just floating around the ocean, photosynthesizing. But they're very important because for all those thousands of millions of years and photosynthesizing, they are producing oxygen and oxygenating the atmosphere, which would set the scene for animal life to evolve. So if it wasn't for them, we wouldn't be here right now. So moving out of the Precambrian and into the Phanerozoic, we have the first era, of the Phanerozoic eon, and that's the Paleozoic. So the Paleozoic ranges from 250 to 550 million years ago. It's known as the age of invertebrates. As we'll talk, there are plenty of vertebrates, but invertebrates, they dominate the fossil record. I mean, invertebrates are the dominant form of animal life on the planet now. Right? Invertebrates are just very successful. It's also during the Paleozoic that land plants evolved, larger animals evolved, fish, amphibians, reptiles at the end. And then there's many extinct organisms from the Paleozoic. And there's a lot of organisms from this period of time that look very foreign to us today. We're not, you know, these animals are so weird looking. And as we'll see, because Paleozoic, complex animal life evolves and appears on the earth for the first time. So it's an evolutionary arms race, right? It's, you know, what traits, what features will work the best. And so evolution is going all different ways until finally what works is eventually selected upon, and a lot of those features that are selected upon in the Paleozoic are still around today. Then moving forward out of the Paleozoic, moving to the Mesozoic, 65 to 250 million years ago. It's known as the age of reptiles. This is the period of time which the dinosaurs were the dominant form of vertebrate life on land. So I know this period is very well represented in pop culture, right? With the Triassic, Jurassic, and Cretaceous. You know, famous actors such as the Tyrannosaurus Rex and Triceratops, Stegosaurus, Brachiosaurus, all of them being present on the Earth during the Mesozoic. And then moving forward out of the Mesozoic, the last era of the Phanerozoic is the Cenozoic, which is 65 million years ago to today. This is known as the age of mammals. So at the end of the Mesozoic, dinosaurs go bye-bye, and mammals inherit the Earth. Right, so mammals, you know, prior to the Cenozoic, they were mostly just rodent-like animals that only would come out at night because the dinosaurs would eat them if they come out during the day, and they're just being held down by the dinosaurs. But once the dinosaurs went extinct, the mammals took full advantage of it, and they diversified, and they became very numerous. So they become the dominant form of land vertebrate during the Cenozoic. And so our history, you know, as we'll see, it spans back all the way to the beginning, but our branch of the family tree really diversifies and branches out during the Cenozoic. So that's it. We have the Precambrian, the Paleozoic, the Mesozoic, and the Cenozoic. All right. So here's a little, here's a geologic timescale with some notable events. So we obviously have the beginning of Earth down here, right? 4.6 billion years ago. The oldest rocks on the planet, 4 billion years old. Oldest fossils, right around 3.5 billion years old. And it goes all the way up here. We have the oldest fish, the Paleozoic. Then we have the dinosaurs go extinct in the Mesozoic, oldest whale, oldest hominids. Oldest hominids, right there, the top line. Basically, it doesn't even fit on here. We're our existence, the period of time which we've been on this planet, even us and our ancestors, our recent ancestors, is so insignificantly small compared to Earth history that it's basically just the black line at the very top. So to help give you perspective as to what happened when this YouTube video puts the 4.6 billion years of Earth history into a 1-minute video. And it's scaled, right? So at time t equals 0, it's 4.6 billion years ago. At time equals 60 seconds, it's today. And as events occurred in Earth history, they come up on the screen and this woman announces it. So you can see and get a feel of what happened and when.
Formation of the Earth. Outgassing of molecules. Formation of oldest rocks. Prokaryotic cell photosynthesis. Photosynthesis by blue-green algae. Eukaryotic cell organisms. Last banded ion formation. Rise of multicellular organisms. Cambrian explosion of waxy-coated algae began to form.
So as you can see, a lot of nothing happened for a very long period of time in Earth's history. It wasn't until about the last 500 million years that life really begins to diversify. Complex animal life just explodes on this planet. Now, it's interrupted by a mass extinction here or there, but yeah, a lot has happened in the last 500 million years. So it's really interesting to think about that. Complex animal life, which we think is a norm, like we think that's that is one of the defining characteristics of planet Earth. It has complex animal life. That's new. That is a new feature to the planet. And it's just weird to think about how it's new. It's been around for about 1/9 of Earth's existence, complex animal life. Yeah, the majority of life on Earth would be characterized by just the proverbial primordial ooze floating around in the tide pools of the ocean. So, what time era has the fewest fossils? So the Cenozoic, Mesozoic, Paleozoic, or the Precambrian? Well, if you answered the Precambrian, you'd be correct, right? The Paleozoic, we have complex animal life, a lot of invertebrates. Then we have, all those invertebrates around in the Mesozoic, but also we have, a lot of reptiles. And then Cenozoic, we have mammals. And there's other organisms around these periods of time, but Precambrian, not a lot of fossils, because just a bunch of microbes and algae. So which letter corresponds to the first appearance in the rock record of abundant fossils? So this is billions of years before present. This is present right here. So first appearance in the rock record of abundant fossils. So if we go back, you see that complex animal life really takes hold. It comes about from the beginning of the Paleozoic, which is around 500 million years ago. So this line actually marks the formation of Earth. Z is probably the oldest rocks. 2.1. This is, we'll learn that's whenever algae appears, photosynthetic algae. Right about here, this is where complex animal life really begins to appear in planet. So that's whenever the fossil record, abundant fossils, become present. So look at this. This is all of Earth history. We think fossils from the past, right? But all fossils we find are from this really short period of time of Earth history, right there, compared to all this, right? All this time, there's not a lot going on in the Department of Life on the planet besides algae and bacteria. So it's amazing. I think these fossils, they're so old. Like, how long ago does this organism live? Well, it's all within that little period of time with regards to Earth history. Now, it's not a little period of time compared, from what we consider to be a long period of time, because it's a little more than 500 million years. So it's been some time, but with respect to Earth history, it's a very short period of time. And so that concludes our lecture on geologic dating and geologic time.